So your book's a little weird in that it talks about the mole and does a bunch of mole calculations and then gets into chemical reactions which don't have any calculations in them, and then gets back into stoichiometry, which is just more mole stuff. So I'm following the book here, but in my classroom, normally I do what would be the equivalent of chapter 11 first, and then do chapter 10. But I didn't want to confuse you. So we're just going to jump right into the idea of the mole and all that kind of stuff. So, up until this point, we talked about atoms, and then we talked in elements and those pure substances. And then in the last unit, we got into compounds, covalent compounds, ionic compounds, that kind of thing. So when it came to counting them, well, how do you count atoms? They're tiny. You can't count them. So the question of like how small an atom was always on people's minds. So, and they were able to figure out atomic mass. Now, the way they did this in the 1800s is they would do reactions with oxygen, and they would see how much mass would be added or mass would be like taken away. So like, for instance, with something like magnesium, you could burn magnesium. And when you burned magnesium, it would get heavier. And that's because it would react with oxygen. Let's write it out. Come on. So you could burn magnesium. Here we go. And with oxygen, that's what it means to burn. And what would happen is your resulting stuff would be, magnesium oxide. But as you can see, the O2 would not show up on the scale. They would, weigh out a certain amount. Say they weighed out exactly 24 grams of this. Well, at the end, you'd have your 24 grams, but there would be this 16 grams added each time. And so the 16 grams, they figured, must have been coming from the oxygen. And this is why charges were called oxidation states, because this 16, this certain mass, which they eventually called the atomic mass or the molecular weight. Sorry about that. Which they eventually called the molecular weight, would always set in these ratios. And that was kind of Dalton and a bunch of others' work where they were working on the law of definite proportions and all this kind of stuff. And then they would come up with things like percent mass and whatnot. So a guy by the name of Avogadro decided he wanted to look into this a little bit more. And he wanted to figure out how many things were actually inside of a substance. So he took this concept, that the idea of masses, and he put it in like chambers. He wouldn't have used balloons, but balloons are a little bit easier for you guys to understand. And what he noticed is that if you put gases into balloons at the same temperature and pressure, so 1 ATM, so 1 atmosphere, we'll talk about pressure more next semester. So that's our pressure. And he would notice that if you put them all at the same pressure and temperature, used 0 degrees C or 273 degree Kelvin, the volumes of all these balloons would be the same. All the volumes would equal each other. It didn't matter which gas you used. If you filled the balloon up to the same pressure and the same temperature, they would all take up the same size. Their difference, though, and he was using glass containers so he could actually measure their masses, is that if you looked at their masses, well, say this, for instance, was hydrogen gas, well, they would have 2 grams, always. And say this, for instance, was, oxygen. Well, it would always be 32 grams. And then say, for instance, this one was chlorine gas. Well, that would be 71 grams. And these things, these masses would always be the same. So how could he take this information, these simple pressures and temperatures and masses and volumes, how could he turn that information into the number of particles that are inside of these chambers? Now, he used glass chambers, I'm drawing balloons. And so basically, it's the idea of pressure. If we have a cylinder here with a plunger, and down in here are a bunch of little balls bouncing around, how hard they bounce up and hit this thing is going to be the pressure inside the chamber. So, more pressure, this will move that plunger up. And the video in the gases is very helpful for this. But you can watch these other videos. I just clicked on it for the periodic table that show that. And then, of course, I should probably put a link to this. Another good example is, or something to check out, is the PhET simulations, which show this pretty well. The problem with the PhET simulations in our Zoom meeting is it's really lagged out. Balloons and buoyancy. They got rid of all the flash ones, which is a real bummer. They went to HTML5, but still. No, we could do that one. Oh, good. It's an HTML5 now. Sure. So anyway, if we have gas in here, boop, 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 you can see these little gas particles are bouncing around, they're flying around. And when they bounce off the walls of their container, that is what causes our pressure. So Avogadro thought to himself, okay, well, we have a problem here. If pressure is equal to force over area, but these areas are all the same because their volumes are all the same, then the force needs to be different. And, force, it depends on, what you're looking at. But we're talking about a force here. Well, we could have force due to gravity. We could have the force due to the balls bouncing off of this thing. So he was able to plug in the numbers for the little individual atoms bouncing off the walls of his container. And when he took these masses, what he figured out was their temperature is all the same. So that means their kinetic energy, kinetic energy, is all the same. But their masses are different. So for them to be moving around like this at different masses, but still have the same kinetic energy, that means their velocity had to be different. And from all of this little data, he was able to come up with the amount of gases, or the amount of stuff inside the chamber. So how many balls were inside that chamber based off of this information. And there's a problem, because if you took gas and you filled it up at 1 atm At 0 degrees C, the volume would always be the same. It would be 22.4 liters. The mass would change. The mass would depend on the gas. So, depends. But when you took all that information and you plugged it in, he called this a mole of gas. He used a different word because he was Italian. This is a German word. It means molecule. When you took this amount of gas and you extrapolated out how many things were inside of there, so the number of things inside of there was 6.02 times 10 to the 23rd atoms or molecules. At the time, they didn't really, because this would be starting in around 1815 is when he's starting to do this work, and he publishes a lot of his work in the 1840s and 50s. It's not widely accepted because this number is huge. This number is ridiculously huge. And the problem with this number being ridiculously huge, that means that these little dots here that are representing atoms have to be so small that in the minds of 1820s, 1830s, 1840s people, well, that just meant they didn't exist. You got to remember, back then, the richest person in the world, you know, kings and queens, they didn't even have $1 billion. First billionaire doesn't come around until Rockefeller. But that's 10 to the 9th. I didn't do a billion. There we go. I did a million. That's 10 to the 9th. Right? And this is 10 to the 23rd. They didn't even think the world was that old. And so the fact that this balloon, which was not very big, you know, he would have used a glass cylinder. It was not very big. Was containing this much stuff was just absurd. And the fact that you could do it for hydrogen, it would equal the same thing as water. And that he suggested that when you split these up, you would notice that you would still get out the same amount. A lot of people didn't like that idea either because of the idea of atoms and molecules being, you know, this extremely nebulous thing, which they didn't like. They wanted them to be real things. Even the design, you know, small little tiny balls that, you know, you could see if you had a good enough microscope. That's what people wanted. And this just completely destroyed them. So to give you perspective on 6.02 times 10 to the 23rd, if we have a graduated cylinder and we fill it up to 18.01 milliliters, that is 6.02 times 10 to the 23rd water molecules inside of that tiny amount of water. It's an extremely small amount. If we were in class, I usually take the 18 mils and I just pour it on my shirt, and then you'll notice that my shirt will get dry within a few minutes. It's just an extremely small amount of water, but that's how many things were inside of it according to Avogadro. And again, perspective on this number, if we talked about money, if I gave you this many pennies, so that would equal 6.02 times 10 to the 21st money. You could spend $1 million a second every day from the day you were born, 24 hours a day, till the day you died at 100, and you would have spent 0.1% of your money. If you had this money in physical money, it would cover the entire earth in about 3 miles worth of money. If you had this many basketballs, you know, basketball, I don't know how to drop basketball, it would be the size of the earth. So this number was huge, and it really, really messed with scientists at the time. Avogadro unfortunately dies in 1853, and his work is basically forgotten for a little bit until John Dalton starts doing his work with poor little computer's not working. He starts doing his work with the definition of the atom, and that is where enter in our little PowerPoint here, where it talks about AMU. We talked about this before, where we talked about, okay, so what are these protons, neutrons, electron things? Like, what is an atom's mass? What is the smallest atom? And the smallest atom was hydrogen. And they said, okay, so what is the individual mass of a hydrogen in AMU? And well, that's 1 AMU, right? But what the heck was an AMU? Remember, an AMU was 1.6 times 10 to the negative 24th grams. Well, guess what happens if you take this number and you multiply it by Avogadro's number? You get 1. So what Avogadro actually found was the conversion factor from AMU into grams. Pretty cool. So when he took a balloon of hydrogen, which is H2, and he had 2 grams of it, well, that meant that he had 2 grams of hydrogen, which is 1 AMU for the one proton, and the other hydrogen has 1 AMU for the other one. So each individual hydrogen molecule would have a total of 2 AMU. But through his work, if you took that number and you multiply it by 6.02 times 10 to the 23rd, and not AMU, but the actual gram number, that's where you get the 2 grams. And Dalton, once they had kind of figured out what the smallest atom's mass was, goes back and he recreates all of Avogadro's work. In his work in trying to become, actually set down the definition of the atom. And he finds out that Avogadro was right, that atoms are that small and that there are that many inside of them, and that they seem to be adding themselves together in these masses that are multiplied by this number. Now that number would be different if they used a different number for mass. So because they were using the gram, you get the 6.02 times 10 to the 23rd. But if we were using ounces, it'd be a different number. If you were to talk to an alien and ask them what a mole was, and you explained it to them, they would be like, oh yeah, that would be this number based off whatever mass their system is. But that's where the 6.02 times 10 to the 23rd comes from. It is the amount of stuff you need to turn the individual atomic mass of a substance into what we call the molar mass. And molar masses were found by experimenters like Dalton and Avogadro by doing those things where they were adding stuff together. So the reason why magnesium and oxygen would always combine in this ratio of 24 and 16 was because magnesium is 12 protons and 12 neutrons, and the oxygen is 8 protons and 8 neutrons. And when those combine together, they weigh, the total amount which is 20 and 20, right? And then if you have 6.02 times 10 to the 23rd of these things, you don't have 24 AMU, you have 24 grand. Same thing with this. You don't have 24 or 16 AMU, you have 16 grams. And so that is the mole. The mole is the amount of stuff that is in 1/12 of a carbon 12 atom. So 6.02 times 10 to the 23rd protons is 1 gram. So 6.02 times 10 to the 23rd carbon atoms would be 12 grams. And 6.02 times 10 to the 23rd helium would be 4 grams. And 6.02 times 10 to the 23rd uranium would be 238 grams. That's what the mole does, is it gives us a way to count atoms by mass. And that's extremely important because without that, it would be impossible to count atoms. And we need to count atoms when we're doing things like mixing stuff together. So let me just give you an example of how we use this in real life. Money. If you're the federal government and you're constantly collecting money, say you've collected $1 billion in your $1 bills that was floating around. Well, if you were sitting down and you were counting that, it would take you a very long time to count. Say, for instance, I locked you in a room and I put the $1 billion in there. Just make a stack of money like this. Money. And you can't leave. Yay. The door behind you will lock and you'll be stuck in there. And I say you have two choices. You can ask to leave and you'll have nothing. Can't take anything with you. Or you can count all the money here. And if you count all of it and tell me the exact amount that's there, you can keep all of it. How many of you would take that challenge? So if any of you took it, you're dead. Because say best case scenario, you're counting this money pretty fast. Well, even if you were counting a bill a second, well, that's 31 years. 1 billion seconds is 31 years. So even if you're able to count this very quickly at like $1,000 a second, maybe you're just super fast, that's still 11 days. So counting these huge numbers is really difficult. But say, for instance, you had a scale in here. It would be very easy to count the money because in the United States, even though we like to use, that's such a terrible word. Even though we like to use the imperial system, our money all weighs 1 gram. Every single one of our bills weighs 1 gram. So you could just take this money and shovel it on here. And you could weigh it. And once you've weighed out 1 billion grams, you'll have counted every single one of those dollars. Will it take you 31 years? Nope. Because who knows? So you can fit, $1 million on that scale. It's got 1 million grams. It'd be hard for you to pick that up, but either way, you could count that pretty quickly. But if you just had to sit down and count it physically, best case scenario, 11 days, worst case scenario, 31 years. You would starve to death inside that chamber. So we had this problem with atoms. You can't count them. it's impossible to count. Look at that number, 6.02 times 10 to the 23rd. Remember, for instance, in our water, we had 18 milliliters of water, which is an extremely small amount of water, and that contained 6.02 times 10 to the 23rd. Well, say I needed to count those atoms. And say, for instance, I had superpowers. On the day I was born, I'm able to count 10,000 numbers a second. 24 hours a day. Every single day. How long would it take me to count this water? Well, we have 6.02 times 10 to the 23rd things, and we can count them 10,000 times for every 1 second. So this will give us our seconds. Well, we want to get rid of seconds. We want to get into minutes. And then we want to get out of minutes and get into hours. We want to get out of hours, get into days, and then we want to get out of days and get into years. So how long would it take us to count to this number? Now, without even plugging in our numbers, I just want to show you something. This is 10 to the 4th. This is 6 times 10 to the 1st. This is 6 times 10 to the 1st. This is 2.4 times 10 to the 1st. And this is 3.65 times 10 to the 2nd. So that's 10 to the 2nd, 10 to the 3rd, 10 to the 4th, 10 to the 5th, 10 to the 11th. And then with all these numbers, we're looking at like 10 to the 12th. It doesn't even cut this in half. We're still talking billions of years to just count the amount of water that's in 18 milliliters. So that's where the mole comes in. 1 mole is equal to 6.02 times 10 to the 23rd things. And if you have 6.02 times 10 to the 23rd protons or neutrons, guess what that equals? 1 gram. So 18 milliliters of water. The density of water is 1 gram per milliliter. So that means we have 18 grams of water. So we have 18 grams. Water is H2O. So that's 1 proton, and then 8 protons and 8 neutrons. So that gives us a total AMU of 1, 2, and then 10, and then 18 protons and neutrons. So we have 18 grams. That's what the mole does. The mole allows us to count atoms using masses. We call this the molar mass, or the mass of something, 1 mole of that thing. So if we look at your periodic table now, instead of looking at every single one of these numbers here as AMU, we can now look at them as grams. And now instead of this being 1 atom of hydrogen, we can think of it like 1 mole of hydrogen. If I have a mole of hydrogen, I have this many grams of it. If I have a mole of lithium, I have this many grams. And grams is the easiest measurement to make. We just throw it on a scale. So if we have, for instance, oxygen gas, well, oxygen gas is O2. So we'll have 2 times this mass. And now if we have compounds, for instance, say we have neon, we just go to our table here. Neon says that it weighs 20.18. So if we have 1 mole of neon, we have 20.18 grams of neon. If we have hydrogen by itself, hydrogen is 1.0 what? 008. We'll just round that to 01 grams per mole. If we look at oxygen, if we have 1 mole of oxygen, that is 15.99. 99999. So let's just call that 16 grams. So now if we're looking at that water molecule, the molar mass of water will be 1 gram for the hydrogen, 1 gram for the hydrogen, and then 16 grams for the oxygen, 18 grams per mole. This is the concept of molar mass. Avogadro discovered that magic number 6.02 times 10 to the 23rd as a conversion for all of these atomic masses becoming molar masses. And then your book might call this what's called a molecular mass, because this is a molecule. So that's all the molar masses added together to what's called a molecular mass. But a lot of the times it's just called the molar mass as well. And so that's why you can see that 24 and that 16 ratio kept showing up when they would burn magnesium. When they would burn aluminum, it was a 27 to 16 ratio. But the ratio was different. We would have, instead of 27, it would be 54, and then instead of 16, it would be 48. So the way it would add it together. And so that's why they knew the oxidation state of aluminum had to be +3 because of that mass ratio addition. So finding molar masses is really easy. Say we had some magnesium phosphate. And the question was, well, how much, what would 1 mole of this weigh? What is the mass of 1 mole of this? Well, we would do magnesium. We would go to our table. Magnesium is 24.3. So 24.3. It says you can do 2 numbers after the decimal or 1. I'm just going to round to 1 for the sake of speed. That's grams per mole, and we have 3 of them. And then our phosphorus here, there are 2 of them. See, that multiplies that by 2. So then our phosphorus is going to be 30.97. So let's just call that 31. So 31 grams per mole. And there's 2 of them. And then our oxygen is 4 here, but then that 2 is going to multiply that. So our oxygen is 16.0 grams per mole. And we don't have 4 of them. We have 4 times 2, so we have 8 of those. And now we're just going to add this all up. So we have 24.3 times 3. And we have 31 times 2. And we have 16 times 8. So magnesium phosphate is 262.9, I think it said. Show me this. Thank you. 9 grams per mole. So if you wanted to count 6.02 times 10 to the 23rd, in this case they're called formula units, but we'll just call them molecules. Molecules of magnesium phosphate, the easiest way to do that would be to go to your scale and weigh out 262.9 grams. That's what the mole does. It lets us count molecules because they're so tiny by just using their masses. So if you want half a mole, you'd get half of this. If you want a tenth of mole, you'd get a tenth of this. It makes it very, very simple to count this amount of stuff. So let's do another example, molar mass. Something simple. Say we had some carbonic acid, which is the acidic flavor in soda when you carbonate it. If you've ever had sparkling water, it tastes sour, and that's because you have carbonic acid in it. So what would be the mass of 1 mole? Well, we'd have hydrogen, which is 1.0 grams, and we have 2 of them. We have a single carbon, 12 grams. We only have 1 of those. And then we have oxygen, which is 16 grams, but we have 3 of them. So this is 2, this is 12, and this is 48. So what is that, 62 grams per mole, right? Did I do that wrong? 12 plus 2 plus 48. 62. You'd have 62 grams per mole. So if you were interested in making some sparkling water or some soda, and you wanted to know how much carbonic acid was in there, you could weigh your sample before and then weigh your sample after you've put your bubbles in it. And the mass added, if it was 62 grams, that means you added 1 mole of carbonic acid. So you added 6.02 times 10 to the 23rd atoms. Pretty cool. So then there's other things that we can do with this using molar masses and stuff like that, conversions and whatnot. Let me give you a little map to help you with conversions today. So if the mole is our center and we want to convert the mole to atoms or molecules or any sort of things, then we can multiply it by the 6.02 times 10 to the 23rd to go that way, or we can divide it by 6.02 times 10 to the 23rd to go that way. Then, if we want to convert from moles to grams over here, we can use the molar mass. And if we go that way, we multiply. And if we go this way, we divide. And then because we learned about Avogadro, he found the mole, and he found the mole when you have a certain amount. So if you want to, you can go to volume using 22.4, multiply, and then obviously divide. So say, for instance, you had, 25 grams of oxygen, and you wanted to know how many atoms was that. Well, we can use dimensional analysis like we used in the previous thing, and we can use our conversion factors. Grams of O2 to moles of O2, and it tells us we should be dividing by the molar mass. So that means 1 needs to go here, and the molar mass of oxygen needs to go here. So we'll put 32, because oxygen equals 16, and we have 2 of them. 32 grams. And then lasso. Move over. There we go. Now, to get out of the mole, we want to use this conversion factor, 6.02 times 10 to the 23rd molecules. So taking 25, dividing it by 32, and then multiplying it by 6.02 times 10 to the 23rd is the number of molecules in a 25 gram sample of oxygen. So we can use this little roadmap here to convert from any number to any of the other numbers with the different units. So if you want to use that today to help you out with your conversions, that can help you out. There are better versions of it online. Obviously, my drawing is terrible, but like mole conversion. That's what I like to call it. And you can see there's better versions of it out there. To help you out. This one kind of shows you going from mass to going through things to going through the cloud, so you kind of see that. And it actually shows you the, rather than like saying multiply, divide, it just shows you the fraction to use. So a lot of helpful things there. So gram formula mass is another way of saying molecular mass. We talked about conversions, we talked about grams, those are a bunch of examples. If this was class, you would do whiteboard practice. When I had whiteboards, now we use it's everyone's cell phones on like a Zoom app or whatever. And then, all right, so that's our concept of the mole. We talked about that. So then, there's a little bit more going on in chapter 10, which talks about percent composition or percent by mass. And then there's what's called empirical molecular formulas. These are all kind of in chapter 10. So what is percent composition? Well, if you have a molar mass, what you can do is you can figure out what are the percentages of the things inside of there. Rather than looking at the actual like mass ratios, you can look at the percentage ratios. So say for instance, we have some water. We already know that water is 18.0 grams per mole. We already did that. But the question is, okay, well that gives us a hydrogen ratio is 2 grams for every 18 grams. Well, look, 1/9, what does that mean? And then oxygen is 16 grams for every 18 grams, which is what? 8/9. So those are ratios. They don't really help us. But if we're talking about percentages, then what we can do is we can figure out, okay, what percentage of the mass of water is hydrogen? So 2 divided by 18. Well, what is that percentage-wise? And then times 100%. So hydrogen is 11.1, or sorry, water is 11.1% hydrogen. Obviously, we can do the math, but you know, we can also just subtract. But 16 divided by 18 is 0.888, so we'll just call that 88.9. Oxygen. So one of the things Dalton found was mass percents, and Lavoisier and a bunch of others, where they would go, okay, well, if we look at the percentages for water, the percent by masses are always the same. Water is always 11.1 hydrogen and 88.9% oxygen. If you don't have those percentages, you don't have water because you don't have the correct mass ratio. And so this is what they're talking about when they're talking about percent composition or mass percent. A mass percent is just one atom, and the percent composition is every atom. So it's two names for the exact same procedure. So that's what they mean by it. So if they say like, okay, say for instance you have say for instance you're going to go get some tungsten ore or some tungsten. So you want some tungsten ore, and the ore, you know, tungsten is very dense, so the ore is going to be very heavy. And so the question is, okay, well, what percent? I'm terrible at writing percent. What percent of the sample is tungsten? If the ore is tungsten oxide, in this case, tungsten 3 oxide. Well, what we would do is we would do our grams per mole of the tungsten multiplied by how many tungstens there are. And then we would do grams per mole of the tungsten oxide. And then we would multiply that by 100%. Well, let's look up tungsten. Tungsten is periodic table down here, and 103.84, so we'll say 103.8. 183.8. So 183.8. We have two of them. And so we're going to multiply that by 2. And then oxygen is 16 grams per mole. And we have 3 of those. So add these together. Clear. 183.8 times 2. And then plus 16 times 3. So this is 415.6 grams per mole. So now we can find our percentage. There is the 183.8 times 2, and then there's our answer. So 367. Yeah. 183.8 times 2. And then we're going to divide that by our molar mass, 415.6, to give us that times that by 100. And we get 88.5%. So say, for instance, you're going mining for tungsten and you find this ore. Well, every kilogram of ore is 88.5% tungsten. So every single shovelful of tungsten ore is almost completely tungsten. So it's very lucrative for you to use this ore because it's very, very high in tungsten by mass. It's one use of it. We use this all the time for determining mining sites. We would go, okay, well, what are the ores in the sample, the soil sample? And say, for instance, you have, you know, some gold ores, or you just have some pure raw gold. well, then you would want to know what is the mass percent or the percent composition of that gold. And as low as if you have 1% gold, you can sell that land claim, not even the land, just the claim to come mine the land for a huge amount of money, because 1% by mass gold sample is just extremely lucrative. And then if you have the same amount of like rhodium, well, rhodium's like $200 a gram right now, where this is only about 53-ish grams per gram, $53 per gram. And this one is about $200 per gram. So yeah, if you were to find like rhodium ores, then that would be extremely lucrative too. And so mass percent is a way to be able to figure that out. And remember, mass percent is just one of them, and percent composition is just both. Now we could do the math and say, okay, well, the percent of oxygen is equal to 16.0 grams per mole times 3 divided by the 415.6. Did I do the right math? Let's do it again. 183.8 and times 2, and then divided by 415.6. I might have been dyslexic. No, I was fine. Okay. And then, so that's that. The other thing we can do is we can just subtract it. Obviously, if we do, 48 divided by 415.6, come on, 48 divided by 415.6, we get 11.5%. But we could also just subtract it from 100, and that's because there's only two things here. This is also another good way when you're smelting the ore. The ore, if it's iron oxide and it's 88.5% tungsten, tungsten oxide, and it's 88.5% tungsten, well, you could throw in 1,000 grams and you could monitor the mass. And if the mass gets to about 885 grams, then you've burnt off all the oxygen. And if the mass starts to go lower than that, then you have some contaminants, or it's too hot and you're boiling off of your tungsten or whatever. The mass percentages become extremely helpful tools for checking this kind of stuff out. So we did examples there. And then finally, the last thing that's in chapter 10, and it's only kind of briefly mentioned and it's kind of difficult, is some forensic science in what's called empirical and molecular formulas. So how were they able to actually find the formulas of things? And the answer was they would do these extractions. So say, for instance, we had magnesium oxide, and we wanted to go backwards, and we wanted to split it up into its magnesium and oxygen. Well, we could do that. And what's cool about that is that these guys are different molar masses. This guy is 24 grams, and this guy's 32 grams. So they're going to move at different speeds because of their different masses, especially if we turn them into gases. So what we would do is, if we could plot it and say this was time, and this was the amount, or in this case, the percentage of the sample, if we looked at this over time, because the magnesium is lighter than the oxygen, we would see nothing for a little while, then we would see a little blip, and then we would see another little blip. And depending upon the mass percentage of this, our blips would be different sizes. So in the case of hydrogen, or this would be our magnesium oxide, in the case of water, we would have a blip right away, and then we would have another blip of the oxygen, where this is our hydrogen and this is our oxygen, if this was percent. And so we would see these blips and say this thing came out at 11.5%, 88.1%, and this blip was 88.9% of our blip, then we could take these numbers and go backwards and figure out the formula. So say for instance, let me get an example, because I can't make these numbers up. It just talks about how to do it. I'm going to show you all that stuff. All right, so that one's ugly. Okay, so say for instance we did that and we have some potassium and we have some chromium and we have some oxygen in our sample. And it says 26.56% of the stuff was chromium and 35.41% of it was oxygen. No, chromium. So this is this one's potassium. And this is chromium. And then it says the rest is oxygen. So let's get out our calculator here. 26.56, and then we're going to add that to 35.41. So then 100 minus our answer, which it just took away. I'm sorry, I'm used to using a different calculator here. All right. So 100 minus 35.41, and then minus 26.56, 38.03. So how could we figure out the formula of this potassium chromium oxygen compound? This is what's called the empirical formula. And so the way to do it is to assume that we have a 100-gram sample, because if we add all these up, we're going to assume that they add up to 100%. So let's just, instead of percentages here, let's just assume grams, because 26.56 of 100 grams is 26.56 percent. So we can figure out the moles. And we do that by going 26.56 grams of potassium is how many moles. So we can use that molar conversion I showed you. And it says to go from mass to moles, we want 1 over molar mass. So 1 over the molar mass of potassium. So let's find potassium. Potassium is 39.09, so we'll just say 39.1. So clear that out. 26.56 divided by 39.1. This is 0.679 moles of potassium. Okay, can't do anything with that number yet. But say now we have chromium and we want to convert grams of chromium into moles of chromium. Go to our periodic table. Chromium is 51.9661, so let's just say 52. And now we can go, okay, 35.41 divided by 52 gives us 0.681 moles of chromium. And then finally, we want to figure out the moles of our oxygen. We have grams of oxygen. And so 16 grams of oxygen for every 1 mole of oxygen. So clear 38.03 divided by 16 is 2.38. So now we have a formula, but it's ugly. It's not a good ratio, 0.67 or 0.68 to 0.68 to 0.38. So what we can do is we can divide all of these things by the smallest number, which we're just going to call that 0.68. And what this will do is it will change our ratios. Instead of this being potassium 0.68, chromium 0.68, oxygen 2.38, well, if we divide this by 0.68, 0.68, and 0.68, then we get potassium at 1, chromium at 1, and I'm going to guess we're going to see this at 4. So if we divide this by 0.68, we get 3.5. So this is going to be oxygen at 3.5. So this would be what we call our empirical formula. But the problem is that you can't have 0.5 of an oxygen. That doesn't make sense. The chances are we need to double everything. And so this is K2Cr2O7, potassium dichromate. We just figured out the formula of this substance from its mass percentages. Pretty cool. So we used the percent composition to give us a mass, and we used our mass to give us a mole ratio, and then we adjusted our mole ratio to give us an empirical formula. And sometimes, for most ionic compounds, the empirical formula will be the molecular formula. But in this case, we had to do a little bit of a trick to it where we doubled it to get rid of that 0.5. Well, say for instance, you're dealing with a covalent compound. Say for instance, we have some carbon, hydrogen, oxygen thing, and we would like to know what it was. Well, hold on one second. Let me get my exact numbers so this works out. Boop, boop. There we go. So say, for instance, we take this substance that contains carbon, hydrogen, oxygen, and we find out that it is 40.0% carbon and that it is 6.7% hydrogen, and the rest is oxygen. So what would be the empirical formula for this substance? So again, we're going to assume 100 gram sample, so this just becomes grams instead of percentages. So a number of moles of carbon will be the molar mass of carbon for every 12.0 grams of carbon. For hydrogen, we have 6.7 grams of hydrogen, and hydrogen's really easy because it's just 1 gram for every 1 mole of hydrogen. And then for the oxygen, we have 53.3 grams of oxygen, and that gives us 16 grams of oxygen for every 1 mole of oxygen. So 40 divided by 12 is 3.33. 6.7 divided by 1 is 6.7. This is moles. And then 53.3 divided by 16 is 3.33. So we have carbon, we have hydrogen, we have oxygen, and we're going to divide them all by the smallest of these numbers. To give us a ratio of 1 to 2 to 1. So our empirical formula is CH2O. But this doesn't look like CH2O. CH2O would be a yellowish liquid. It would smell. It's basically formaldehyde. And what we have is a white sugary substance. So what we do is we heat it up to figure out what its actual molar mass is. And what we find is that the actual molar mass is equal to 180 grams per mole. But this thing's molar mass would be 12, 1 times 2, and oxygen is 16. This thing's molar mass would be what? Can't think right now. 30. So to figure out the actual formula, what we do is we take to figure out what we call the factor, we take the empirical formula's molar mass, we divide it by the actual formula's molar mass, and this will give us our factor. So in this case, our empirical formula was 30 grams per mole, and our actual was 108 grams per mole. To find the actual, you'll have to do an experiment, so it has to be given to you in the problem. So look for it in the problem. And this gives us a factor of 6. Because 30 divided by, flip this over, because again, I'm having a hard time here with my brain. Our factor is equal to the actual divided by the empirical. So in this case, 180 grams per mole divided by 30 grams per mole. And that equals 6. So our real formula is going to be 6 times bigger. So C6H12O6, which is glucose, which would explain why this stuff looks like sugar. Now, that's all the stuff that's in chapter 10, and if my explanations were a little long and wordy and it was hard to follow, then remember that the module has every single one of these things broken down into its individual little videos. And then on top of that, if you want to see more examples, if you see any of these videos that say by me, that'll be a video of me actually doing a example from homework that I had for another class. So you can click on this and then it shows you like, okay, here's an example of a problem, and then you can watch it. And these videos are very short. They're like 3-4 minutes long at the most. And that's everything from chapter 10. Any questions before we move on? Or before we end today? Okay, I'm going to hit stop record.